Have you ever wondered how our body produces energy? It's a question that's as fascinating as it is complex. Energy is at the heart of everything we do. It's what gets us up in the morning, helps us think, move, and even dream. The primary source of this energy is a process called the Krebs cycle. It's a fantastic, intricate system that keeps us going, turning the food we eat into the energy we need. Intriguing, isn't it? Well, today we delve into the Krebs cycle, the powerhouse of our body. So everything begins with a molecule of acetyl-CoA. Now imagine this molecule as a tiny buzzing bee full of potential energy. This bee, or acetyl-CoA, is a 2-carbon molecule. It's about to embark on a grand adventure, and its first step, it combines with a 4-carbon molecule. This fusion is like a dance where two individuals merge to create something even more beautiful. The result? A 6-carbon molecule known as citrate. But this dance doesn't happen spontaneously. It needs a little help, a catalyst, if you will. Enter the enzyme, citrate synthase. Think of this enzyme as the matchmaker, the one who orchestrates the dance. It facilitates the reaction, ensuring that our 2-carbon and 4-carbon molecules can join together smoothly and form citrate. And that, my friends, marks the beginning of the Krebs cycle. But hold on, there's more to it. So stay tuned as we delve deeper into this fascinating process. From a 6-carbon molecule, we now move to a 5-carbon molecule. We left off with citrate, a 6-carbon molecule which is about to undergo a transformation. This change is facilitated by the enzyme aconitis. Aconitis rearranges citrate into a molecule called isocitrate, still with 6 carbons. But here's where things get interesting. Isocitrate is now exposed to a new enzyme, isocitrate dehydrogenase. This enzyme does two things. First, it removes a carbon from isocitrate, which is released as a molecule of carbon dioxide. This reduces isocitrate to a 5-carbon molecule known by the tongue-twisting name of alpha-ketoglutarate. But isocitrate dehydrogenase isn't done yet. Its second job is to strip away a pair of high-energy electrons which are shuttled off to NAD+, a molecule that acts as an electron carrier. In the process, NAD+ is reduced to NADH. This NADH is a valuable source of potential energy, a battery of sorts, storing energy for later use by the cell. So, to recap, citrate has been transformed into alpha-ketoglutarate, a process that required two enzymes, aconitis and isocitrate dehydrogenase. Along the way, a molecule of carbon dioxide was released and NAD+ was reduced to NADH. So far, we have seen two enzymes and a range of molecules, but wait, the story isn't over yet. Finally, we return to where we started. Our alpha-ketoglutarate molecule is ready for its transformation. With a little help from alpha-ketoglutarate dehydrogenase, it's converted into succinyl-CoA. Now, succinyl-CoA synthetase jumps in to turn this into succinate, a process that generates a molecule of ATP, the cell's energy currency. But we're not done yet. Succinate dehydrogenase transforms succinate into fumarate, producing Phage2, a crucial player in the electron transport chain. Fumarase then steps in, converting fumarate to malate. Our final actor, malate dehydrogenase, takes the stage to convert malate into oxaloacetate, generating another molecule of NADH. And guess what? Oxaloacetate is the very molecule we started with, ready to begin another round of the cycle. Throughout this journey, we've also released carbon dioxide, a waste product which we breathe out, and voila, we have completed a turn of the Krebs cycle. So what did we just witness? We've journeyed through the complex but essential process of the Krebs cycle. It started with the humble acetyl-CoA, combining with oxaloacetate to form citrate, catalyzed by citrate synthase. From there, isocitrate was created, then alpha-ketoglutarate, thanks to the enzymes aconitis and isocitrate dehydrogenase. The cycle continued with alpha-ketoglutarate transforming into succinyl-CoA with the help of alpha-ketoglutarate dehydrogenase. Succinyl-CoA then changed into succinate, facilitated by succinyl-CoA synthetase, before being converted into fumarate and then malate, driven by succinate dehydrogenase and fumarase. Finally, malate was converted back to oxaloacetate through malate dehydrogenase, ready for another round. Throughout this cycle, we saw the production of energy-rich molecules like ATP and electron carriers like NADH and Phage2. These molecules are crucial for powering the body's numerous functions, from muscle contraction to nerve transmission. And that's how our body produces energy, one Krebs cycle at a time.